Thanks.
Yeah. Okay. So thank you so much for coming to this seminar. So yeah, I'll be discussing about about invariant distances and some simple concepts. Okay. So let me start with the. let me start with the Poincare distance. So Poincare distance, it's just 1/2 of log of 1 plus mod z minus w by 1 minus w bar z and 1 minus divided by 1 minus the Mobius map. The Mobius map means modulus of z minus w1 minus w bar z. That's called Mobius map. So this is a point. There are many ways to define Poincare distance. The one natural way to define Poincare distance via this was Pick lemma. So I'm not going in that direction. So I just define directly what it is. So then my aim is to more extend. My motive to discuss the invariant distance on the higher dimension. Okay. So yeah, this is the definition of the Poincare distance. So we'll see some properties of the Poincare distance. The very first property is it's a complete distance function, and it induces the Euclidean topology. In fact, it's a ball with respect to the Poincare is same as the Euclidean ball. Okay. So these are the very nice property about. This is a very nice property about Poincare distance. And next nice property is that the Schwarz-Pick lemma says that Schwarz-Pick lemma by Schwarz-Pick lemma one can we conclude that the holomorphic self maps are semi-contraction. In fact, biholomorphisms are in distant preserving maps. Okay. So the next one is about the geometry properties of the Kobayashi distance. So we are in the metric space. So one can be discussed about geodesics. So you can ask what are the geodesics in the Poincare model. So the geodesics, geodesics of the Poincare model are the Euclidean diameter of the unit disk, and that intersect with the unit disk of Euclidean circle orthogonal to the boundary. And the existence of the geodesics is very nice here. So it's a existence and uniqueness. So if you have a pair of points, you can find a unique geodesics connecting them. So in fact, the geodesics to be smooth here. Okay. So these are the these are the particular nice properties of a Poincare distance. There are many, but I am not going into that. So next I will discuss the Kobayashi and uh, carothodary distance in the higher dimensions. Yeah. So invariant distance. So one of the invariant distance is carothodary distance. So let me start with a complex manifold, and the carothodary distance between any pair of points is realized by the supremum of the Poincare distance. So corresponding image. So the supremum varies. So overall holomorphic maps from X to D, and you just compute the Poincare distance between the images of the points X comma Y. Okay, this is a pseudo distance, and one can conclude that it's a invariant under biholomorphism, which means it's a biholomorphism of biholomorphism of a two manifold. It just distance preserves. Okay, and the carothode pseudo distance become true distance if and only if there is a non-constant bounded function on the space. If you have a space which has only constant holomorphic function, so the functions of reference codomain to be C. Okay. So if you have a only holomorphic function and the domain is constant, then the carothodary is identically zero. Okay. So these are the equivalent condition when the carothodary become true distance. Okay. So for example, if you take omega to be C and C minus finitely many points, and even fact any compact manifold, then C omega is zero, because the only bounded holomorphic function C to D C is just constant. In fact, any holomorphic function on a complex manifold is just constant. Okay, and the C minus finitely many points, you can just since it's a bounded. I mean, the only bounded holomorphic functions are constant because all the points becoming a removable singularity, so that you can get a uh, entire function. Then usually always around one can get C omega 0. Okay, so in fact, this is true for Cn. So I just restrict myself in the C for simplicity. Okay, so now one can we define the dual object corresponding to the cathode is the following. So now in the cathode we just taken supremum, right? So here we are considering infimum in different ways. So this function is called Lempert function. So Lempert function is Lempert function of a pair of points is just defined by infimum is uh, considering uh, considering the holomorphic disk. I mean, holomorphic maps from D to open disk to the manifold, and if the point, if the image containing X and Y, if we take their pre-images, consider the Poincare distance of their pre-images. So if the infimum is overall the holomorphic function from D to X, then this function is called the Lempert function. Okay. Is it okay? Any doubts so far? Doubts, comments so far?
So just one a small comment. So
Yeah.
it's just as a little bit I am not really sure. So mathematically, so because I simply actually never look at the proof of it. So I completely agree that the characteristic pseudo distance. So if there is no non-constant bounded Horner function, then by the definition it's defined as such as a supremum. Yeah, so it cannot be distance for sure, as long as there's no non-constant bounded homomorphic function. And the converse like the direction. So let us just let's just see. So what I said is if there is no non-constant bounded holomorphic function, then by its definition, the CX cannot be distance for sure. That's clear. So now
Yes, yes.
let's just assume so if the CX distance is not a true distance, so that's now the assumption. But still, I think it's literally just logically possible that there could be non-constant boundary function, but the gradient behaves something weird, kind of. So one direction is still
Uh,
just unclear. You might be eventually correct, but I think it's quite non-trivial. You know what I mean?
yes. So I need to write more precise here. So
Yeah,
we
yeah,
need
yeah.
to
I
fix a
understand.
point P comma
Yep,
Q, then C of X comma CX of P comma Q greater than 0 if and only if there is no non-constant bounded
exactly.
function containing, passing through these two points. So I supposed to mention like
Yep,
that.
yep,
Maybe,
yeah.
yeah.
For that part, I
Thanks
agree.
so
Yep.
much.
Hmm.
Yeah, yeah, yeah. Yeah. So I need to start with the points, pair of points. I suppose not start with the generally. Yeah, because otherwise what you
Yep,
said is
yep.
correct.
Very understandable. Yeah,
Yeah,
absolutely.
thank you so much.
Correct.
Yeah. Okay, so the Lempert function is this. So yeah, so we have a carothode Stoddard distance Lempert function. One can we ask whether the Lempert function becomes Stoddard distance or not. So actually, the Lempert function is not a Stoddard distance. In fact, it satisfies it satisfies the positive. I mean, so non it satisfies the non-negativity and the symmetricity clearly, right? So the triangle inequality is the difficult part here, but the Lempert function does not satisfy the triangle inequality. Okay, so for example, if you consider uh, omega to be z comma w and c2, if we consider mod z w less than 1 and mod w less than r, where r could be bigger than 1. So if you consider this domain, one can, if you consider the point 0 comma 0, 1 comma 0 and 0 comma 1, one can we prove that the L omega of the distance of 0 comma 1 comma 1 comma 0 greater than the L omega of 0 comma 1 and 0 comma 0 and plus L omega of 0 comma 0 and 1 comma 0. This is just simple computation. I'm not going to do here because the L omega of 0 comma 0 and 1 comma 0, if you compute this distance, it becomes 0. This is 0. And this becomes is non-zero. So if you compute. so that this inequality will follow. Okay. So this is a little standard example. So even if even if our domain to be more, I mean, our domain to be even if our domain has more regularity condition like pseudo convex, something like that, still this Lempert function does not satisfy the triangle inequality. So that's why people interested into Kobayashi pseudodistance. That's why I'm calling Kobayashi pseudodistance so special here. Okay. Yeah. So now we'll look at what is Kobayashi pseudodistance. So Kobayashi pseudodistance is just influencing finite sum of the Poincare distance between chain of holomorphic function, like fj from unit disk to x, fj of beta j minus one of x means it just look if you consider the I mean if you have a x comma y, maybe I didn't connect it tab. Actually, my tab is not working good. That's why I'm not able to write. I made a PPT. Okay, fine. So if you consider pair of points, let's say this is my disk. Let's say this is my disk. This is my space x. This is x and y. Okay. So what I wanted to connect this x and y by a chain of holomorphic disk. So holomorphic disk means the holomorphic map from unit disk to x. Okay. So I wanted to connect this. So what I'm doing, I'm starting with the holomorphic function from here like this. Okay. Start with the holomorphic function here, and this is f1. F1 connecting this point to this point. Okay. And F2 connecting this to this, F3 connecting this. So I have a chain of holomorphic disks. Okay. I'm taking a point correct distance between these 2 points. I mean, okay, these are the pre-images of the holomorphic disk. Okay. So connecting this point always maps to X, this point always maps to Y. Okay. Got it? So I'm just kind of connect. I mean, I'm just taking the sum of the consecutive points, sum of the point distance of the consecutive points. Okay. So if you take this such a number such a number for all holomorphic disks, all holomorphic chain of disks, then we'll get a Kobayashi. So that is okay. Is it clear? Yeah. So yeah, so it is a pseudo distance, and it's a when it becomes a true distance, then we say such a manifold is called hyperbolic. Okay, some people used to call Kobayashi hyperbolic. I just going with the hyperbolic, and in this case, whenever you have hyperbolic manifold, hyperbolic means with respect to Kobayashi. Whenever whenever we have a Kobayashi hyperbolic, then that the Kobayashi distance function generate the Euclidean topology, maybe the manifold topology. Okay, the Kobayashi distance generates the manifold topology. That's one of the beautiful property. Another property is that another characterization is that this becomes complete if and only if each Kobayashi ball is relatively compact. In general, what when the completeness need not implies the each Kobayashi balls is relatively compact. Okay, the other way is true for all metric space, but another the completeness need not imply all Kobayashi ball is not a relatively compact. But in Kobayashi it is true, but in Carathodid it is not always true. So in some other properties there will be another research going on in beginning of this. Okay, so yeah, so the so now we have three functions. One is Carathodid function and a Kobayashi function, Lempert function. So all three functions satisfies this inequality. It's just they are the contractions. Holomorphic functions of contraction with respect to Kobayashi, Carathodary, and Lempert. Okay. So in fact, if they are invariant under the biholomorphisms. Yeah. So now, if you start with a complex manifold and if you have a pseudo distance on X, just to pseudo distance. Suppose any holomorphic map from the unit disk to the manifold, if you have these properties. Okay. the if you have the any volumer from the unit disk to X satisfies the contractive property, then that pseudodistance is always smaller than the Kobayashi. So this means that Kobayashi is the largest pseudodistance on the manifold, on the complex manifold, with satisfying the contractibility with respect to the Kobayashi distance in the codomain uh, and the Poincare distance on the domain. Okay, so this says that Kobayashi is the largest domain, and then the other way is if you any holomorphic function from the manifold to unit disk satisfying the contractibility, then we'll get Kobayashi is always smaller than the pseudo distance. So here says that Caratodi is the smallest one, which satisfies this property. Okay, and now we can conclude that Caratodi is the smallest one, smaller than the Kobayashi. From here, we can conclude that Caratodi is smaller than the Kobayashi, right? And Caratodi is a pseudo distance that will behave with the Poincare distance. Then via this property, one can we conclude that Caratodi is always lesser than the Kobayashi. Okay. So another simple fact, when we restrict to the Kobayashi and Caratodi and Lempert with the unit restrict to the unit disk, they are coincide with the Poincare distance. So these are this one of the nice properties. So when you restricted with the unit disk, that all pseudo distance becomes all three pseudo distance becomes same. Okay. In general, yeah, the Caratodi is always smaller than the Kobayashi always smaller than the Lempert. So one can say in some people are defining Caratodi in terms of the Lempert. So how they will define is the Caratodi pseudo distance is the largest pseudo distance function, largest pseudo distance, which is the largest pseudo distance, which is less than the Lempert. And sometimes they will call that it's the largest minor on top the L of X, which satisfies the triangle inequalities. Because LX is, Lempert does not satisfy their triangle inequality for a domain, even for domains. Okay. Yeah, so these are the nice properties, and from here we'll see one more nice properties about Kobayashi. So here Kobayashi distance is behave well with the covering space. So if you have a covering manifold, let's say M tilde, and if you pick pair of points, and if you take the pair of points and you consider the one preimage of the point P, then the Kobayashi distance in the bottom domain. So you have this is the manifold, and this is the covering. So that the Kobayashi distance of a Kobayashi distance between P comma Q is you can get infimizing the all possible fibers over the over two over the over 2 points. If you take infimize, then we'll get the Kobayashi distance between 2 points. So let's say I may confused here. We'll start with the manifold and last start with you have a covering space. Take 2 points here, 2 points, and look at their fibers. Compute Kobayashi distance on the Kobayashi distance of M covering space between any 2 points in the points in the fiber, one fiber to another fiber. Then take all infimize, you will get the Kobayashi distance between these pair of points. Okay, the same formula will true for the Lempert. Okay, the same formula is true. This formula true for only Lempert and Kobayashi, not for Carathoid. Okay, and one nice property is this: whenever M is hyperbolic, so does M tilde. Okay, so similarly, completeness also will follows. In fact, so a Riemann surface is Kobayashi hyperbolic if and only if it is hyperbolic in the context of Riemann surfaces, which means that its universal covering space is the open unit disk. So note that. So how we can prove this? Maybe I'll give this a two-line. I mean, it's not two-line proof. It just there is a big theorem is playing behind of this lemma. It's called a uniformization theorem. So any Riemann surfaces, take any Riemann surfaces whose universal cover space is either C hat means Riemann sphere, and the unit disk. Okay. So the Kobayashi distance on C hat is identically zero. So the their C and C hat is not a hyperbolic domains, right? So they are not hyperbolic. So the only hyperbolic uh, simply connected Riemann surface is unit disk. Okay. So where a Riemann surface is Kobayashi hyperbolic if and only if its universal cover space is the unit disk. Okay. This is another nice properties. So okay, these are things I need to discuss some properties. Okay. So I just wanted to go. Now we'll see some examples. So now C hyperbolic domain, which means that cathode ray distance become true distance. Okay. So C hyperbolic manifolds are hyperbolic manifolds, which means Kobayashi hyperbolic. Because C always lesser than the Kobayashi, right? Cathode ray always lesser than the Kobayashi. So cathode ray hyperbolic always um, Kobayashi hyperbolic. The converse is not true. For example, omega minus 0, comma 1. So this is a Riemann surfaces, and its universal cover space is the unit disk. Okay, its universal cover space is the unit disk. So unit disk is hyperbolic, then it is hyperbolic. So Kobayashi, but it is not a cathode hyperbolic because cathode ray pseudo distance on this omega minus 0, comma 1 is identically 0. Is it clear? Any doubts so far? If I'm little speed, then please stop me. I will discuss slowly. Okay, I don't have to write all those things, but okay, thanks. So yeah, next huge class of example is this. All bounded domains are C hyperbolic domains. In fact, it's C hyperbolic domains are Kobayashi, then all bounded domains are Kobayashi hyperbolic. The proof is here. So start with the bounded domain, and the definition is mod z less than or equal to m for all z in D. Then if you start with a pair of points, x comma y, and whenever two vectors is different, then one of their corresponding coordinate, one of its corresponding coordinate to be different, right? So let's say xi is not equal to yi. Now consider the projection map, projection over the projection, and some kind of bounded projection maybe. Z goes to zi by m. So this is the non-constant holomorphic functions, which map from the domain to unit disk, right? So holomorph from the domain to unit disk that separates the point x comma y because so the f of x and fi of x always not equal to fi of y. So this gives the distance. This gives the point correct distance between fi of x comma fi of y is non-zero, which is strictly positive. Then the tx of cd of x comma y is strictly positive. Okay. So one of the class of example. So other class is this. Suppose if you have a if you have a hyperbolic or respectively C hyperbolic, then any open subset of X is also hyperbolic. I think yeah, any open subset of X is also hyperbolic. I think here I suppose to consider any open connected subset of X is also hyperbolic. I mean, open subset will work, I guess. Yeah. So any open subset of hyperbolic manifold itself hyperbolic because if you start with the open set and we have a manifold, now look at the inclusion map. Inclusion map becomes holomorphic, right? So just for the holomorphic maps are contraction with respect to the Kobayashi and cathode whatever. Then from that one we can conclude that open subset of a Kobayashi or carothode hyperbolic is of Kobayashi hyperbolic or carothode. Okay, some example. So now we can look at the concrete example. Okay, so now look at the point polydiscs. I mean, one we can try to conclude the Kobayashi distance between Kobayashi distance and some special domains. Okay, so even the Kobayashi distance is it's a constructive definition involving a chain of disks. So it's very difficult to construct. I mean, very difficult to give a explicit formula in for an arbitrary domain. So we can look at some we can see the formula for the Kobayashi distance on some special domains. Okay. So now first example is polydisk. So now polydisk is the take any point Z and look at the map TZ. TZ with respect to this is the automorphism of the polydisk that takes Z goes to zero, zero vector. So now this can be concluded very easily that the Kobayashi, and this is not a B, I think it's not a, it's KDN, it's a typo there, okay? So Kobayashi between Z comma W, just you can write omega of 0 comma TZ of W in supna. Okay, this you can conclude, this property you can conclude. And if you know what is the point carry distance between 0 comma TZW, norm of TZW, just the tan inverse. Maybe there we have seen 1/2 log over something like that. So that you can equivalently you can write tan inverse of tan inverse of Mobius distance. Okay. So here just one point is 0, another point is somewhere non-zero vector. Then the omega of 0 comma t norm of TZW is equal to tan inverse of norm of TZW. Okay, this norm is just supnorm. So the supremum of all the supremum of the image of images, supremum of the all the coordinates in the image vector. Okay, it's just equivalent to saying that maximum of the omega of the Z comma W. Okay, so the Kobayashi distance of Z comma W is just equal to the maximum of the Kobayashi distance between their corresponding coordinate. I mean, Poincare distance between their corresponding coordinates, right? These are the one example, and this is the one, or these are the one example, and another example is polydicts. But actually, this is not the. I mean, this involves more farm. I mean, this involves this is not that much easy to prove all this. And it consisting more computations to prove all those things. So I just state it simply. So start with a point in the Euclidean ball and consider the psi A of Z. This is a automorphism of the ball. Okay, so where PA is the projection onto the span, complex span A, the vector A, and QA is the orthogonal projection onto the span A. Okay, so now this map is takes unit ball to unit ball, and it has a self inverse. This map has a self inverse. Now, if you compute the Kobayashi distance between these 2 points via, if you have a automorphism, then the same way you can do. So the Kobayashi distance between Z comma W, you can write the omega of 0 comma norm of, there we have different psi Z of W, right? Psi Z of W with respect to 2 norm, then you can get this. Okay. Okay. Because yeah, this will get. So just you can notice one thing here. We have discussed only polydisk and Euclidean ball. These are the unit ball with respect to some norm, right? Unit ball with respect to some norm. So we can discuss unit norm ball. So if you start with a semi-norm, suppose you have a semi-norm on the Cn, and the unit ball is given by this set of points in Cn, then Q of Z less than 1. Then CB of 0 comma Z always KB of 0 comma Z. I mean, the Kobayashi distance coincide with the carothode and Lempert and Poincare, where the one point is 0 and another one is arbitrary point. Okay, So this is true for this is the Kobayashi Karatodiri Lempert Poincare, they are coincides only and only the points 0 comma something 0 comma some arbitrary point in the unit ball. Okay, but not all para points. Okay, but you can make it if you add one more hypothesis into the domain, you can conclude that these all things are equivalent on the domain itself. Okay, so that is furthermore, if automorphism acts transitively on the ball, if the automorphism groups acts transitively on the ball, then the Kobayashi, the carothodary, just you can make it the carothody between 2 points, just you can make it CB of 0, comma P set of W, right? So this is coincide with this Kobayashi, right? By this fact. Got it? So on this fact, then this is just same as the KB of set comma W because automorphisms of invariant under Kobayashi, I mean carothodic Kobayashi Lempert, right? So similarly this. Okay. So this says this Kobayashi Lempert uh carothody Poincare and Poincare with something special. This is not this need not equal to the omega of something else. Okay. Okay, so yeah, ultimately what we can say is Kobayashi carothodic Lemperts always coincides when on the unit norm ball if the automorphism group is acts transitively. Okay, so so you can compute for these three class of domains. Even there is a more class of domains called symmetric domains, something like that. You can compute it, and even you can compute the symmetric by this as well. But there are many, but there will be challenging. So in general, the obtaining explicit formula for the Kobayashi distance is extremely challenging rather than studying its properties because of the definition is the construction of the definition just involving all possible chain of holomorphic disks. So the one can you here in this point we can ask one question that is it possible to define Kobayashi distance between 2 points in D in terms of a single analytic disk joining them? So here we have a chain of analytic disk. I mean, sorry, here analytic disk and holomorphic disk are same. Okay, as per my definition, according to me, the holomorphic and analytic disks are same. So the question is it possible to define Kobayashi distance between 2 points in D in terms of a single analytic disk? I mean, yes, the answer is positive. Start. What happens if Lempert is pseudo distance? So in general, we have seen that the Lempert is not as Lempert does not satisfy the triangle inequality even if the domain is pseudo convex. So what happens if the Lempert satisfies triangle inequality? So then it becomes a pseudo distance. Then the Lempert is always coincident with carothode, right? Because we have seen that carothode is the largest minorant of the Lempert, which satisfies the triangle inequality. Okay, so if the Lempert is a pseudo distance, then will get an answer to the above question, right? The Kobayashi distance pair of points because the Lempert how we define the Lempert function just infimizing omega of the zeta 1 comma zeta 2 where there exists a holomorphic function which maps that zeta 1 takes to point z and zeta 2 takes point y, sorry, w, is it? So you can define in terms of a single analytic disk. You can define the Kobayashi distance in terms of single analytic disk. Okay, for example, so we have a Lempert theorem. So if you have a complex manifold which is biholomorphic to convex domain, then Kobayashi Lempert carothode all are same. Okay, so in this case, Lempert become a pseudo distance. And another example is if you take planar domain, any planar domain, the Lempert always coincide with the Kobayashi. So start with I mean, in this planar case, the proof is simple. So if you take C and C star, C and C star represents a punctured plane. Okay, so C and C star, the Kobayashi, the Lempert function is identically zero. Okay, that can be proved. That you can prove easily. So Kobayashi and Lempert is always zero on the C and function plane. Okay, but look at all other domain. So we have seen that if you have a Riemann surface is hyperbolic if and only if its universal cover is the unit disk, right? So if you take any planar domain other than C puncture plane, whose universal cover is the unit disk, right? Then 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 the formula given by the covering map says that the Lempert is actually pseudodistance, which means the Lempert function satisfies the triangle inequality. So at least the planar case, the Lempert and Kobayashi is always coincide. Okay. So another natural question is this: on which domains or complex manifold does the Lempert function satisfy the triangle inequalities? So this is the one difficult question to analyze. I mean, and this is the, I mean, I guess I was not say difficult, but there are class of domains which satisfy triangle inequalities, but it's very less class of domains. Okay, yeah, fine. So these are the questions I have in mind, and in this direction, I got another. I got a paper to read about it. So it's called the concept is called Kobayashi simple. So now we see what is Kobayashi simple. So if you know this, in this direction, we'll answer to the above question for particular case of uh, uh, domains where the Lempert function satisfies the triangle inequality. Okay. So now what is Kobayashi simple here? So we call a point P Kobayashi simple if P as a neighborhood in which any other point Q, the distance between P and Q realized by the Poincare distance and the single analytic disk that joins P and Q. This means that the Lempert and Kobayashi coincides, at least locally. Okay, we say a point is Kobayashi simple if P is a neighborhood in which the distance between the point and any other point in the neighborhood, the Kobayashi distance between the point P and any other point is always coincide with the Lempert distance of the point with the another point Q. Is it clear? Is it clear the definition? Okay. So as you and again you can see the example is very simple. I mean, some simple example is convex domains are Kobayashi simple because uh, Lempert theorem, right? So Karatoderi, Kobayashi, Lempert all it's a coincide in the convex domains. And another class of example is the product of holomorphic retracts of the Kobayashi simple domains are again Kobayashi simple. Okay. So here I think I don't know I'm skipping to explain. I mean I don't wanted to what's the time now? I have 20 minutes, so I will stop. I will not explain what is holomorphic retract. I will move further. Okay. Yeah. So product and holomorphic retracts of a Kobayashi simple domains are again a simple domain. Okay. So now we see the necessary condition. And yeah, in fact, one more definition is there. We say a domain to be Kobayashi simple if every all points are Kobayashi simple. Okay. Yeah. So now we see the necessary and sufficient conditions when a point is, sorry, we see the necessary condition when a point is Kobayashi simple. The, the set IP, which is called Kobayashi indicatrix, is called the Kobayashi indicatrix, collect all the vectors in the tangent space. I mean, here D is a domain, then the tangent space is Cn. Okay, so collect all the vector in Cn, compute some quantity which is less than 1. So this set is convex. I will explain next what is that quantity is. So this set is convex. Okay. So this is a necessary condition. So this is called and this set is called the Kobayashi indicatrix. So if the Kobayashi indicatrix is convex, I mean, if your point is Kobayashi simple, then the Kobayashi indicate must be convex. Okay. Yeah. So now I will define what is that quantity gamma p comma v. That's a Kobayashi infinitesimal pseudo metric. So this Kobayashi infinitesimal pseudo metric is just start with a manifold and a point and a tangent vector. The Kobayashi pseudometric, I mean, Kobayashi-Rydon pseudometric, sometimes people used to call as Kobayashi-Rydon pseudometric, is defined as gamma m of p v. So the point and consider the tangent vector. Okay. Now we have a tangent vector. Look at the tangent vector and the influencing all possible r such that the volume, I mean, they are influencing some quantity. What is that quantity is uh, uh, the the smallest radius one can hit by a holomorphic. I mean, one can smallest radius r such that the tangent vector tangent vector of the image tangent vector of the image point. I mean, am I right? Or geometry is, I think, is not the correct way. Uh,
Yeah, I think it's okay. Yeah.
yeah, I mean, yeah. So influencing all possible radius, I mean, all radius are just you can scale by a that you are reproducing the tangent vector by a holomorphic disk. Is that clear? Just there exists a holomorphic function, and that holomorphic function takes 0 to p. And if you consider the derivative at that origin, if you hit the derivative at origin means the derivative f dash of 0 of 1. So we are that's I mean decided. I mean that is called the derivative at origin that takes r to be the given vector b. Okay. So it's scaling how far. I mean, you wanted to you wanted to influence the radius such that you have to reproduce the vector v via the holomorphic disk. Is it clear? And if you have this pseudometric, I mean, pseudometric means it has to satisfy uh, two properties. One is non-negative, and another one is positivity. I mean, sorry, non-negative. And the another one is if you take gamma p comma alpha v, it just is equal to modulus alpha times of gamma m of phi comma v. Okay. The homogeneity is must satisfies. And one more thing is triangle inequality here. Triangle inequality means gamma m of phi v plus w is always less than or equal to gamma p comma v plus gamma p comma w, right? So these are the pseudometric in terms of tangents, in terms of point and tangent vector. So now here we can define if you have this measurement measure. I mean, if you have measurement of, I mean, if you know the measure of a vector, then you can define a length of the curve, right? So start with a C1 smooth curve. Look at the length is just integrate 0 to 1, and the gamma m of sigma t and the gamma prime of t into dt. This is the length of the C1 smooth curve. Now you can define, you can take any pair of points z comma w. The one can you define a pseudo distance dm comma z comma w, just influencing length of the all possible curve joining those 2 points. All possible C1 smooth curve joining those 2 points. So this becomes a pseudo distance, and when if D is a domain, then this distance and the carotheric distance coincides. So when you can produce a carotheric distance via the integrated form, integrating the Kobayashi pseudometric, and you will get a length, and if you messing those length, you will get the carotheric. Sorry, Kobayashi. Okay. So here the gamma m is the uh, this quantity. So IP is a set of all vector, then the Kobayashi pseudometric. I mean, if you take all possible tangent vector, then Kobayashi pseudometric is less than one. Okay. So if you consider this set is should be convex. Okay. So this is a necessary condition when we are point to be Kobayashi simple. Yeah. So this is, I mean, there are small properties, and I'm skipping the small properties because I cannot finish this within 1 hour if I explain all those things. Maybe, yeah, we see. So the MOI Pan in 1994 years proved that suppose you have a Kobayashi metric gamma and a complete Kobayashi simple domain. So here complete means complete with respect to Kobayashi distance. Every sequence is convergent, right? So, and if you have a complete Kobayashi simple domain, and if you have a Kobayashi metric and a complete Kobayashi simple domain is a penciler metric. Okay, this in a penciler metric, then the distance, the Kobayashi and the Lempert always coincides. Okay, so the Kobayashi simple makes Kobayashi simple says that Kobayashi and Lempert coincide at least locally. But yet this theorem says that it always coincide with the Kobayashi always coincide with the Lempert throughout the domain. Okay, so I'm just skipping what is penciler metric. Maybe I will leave it to you guys. Okay, so these are the one way. These are the class of examples. So okay, you can ask here why I'm interested to define Kobayashi simple, all those things. So as I said, obtaining the explicit formula for the Kobayashi distance explicitly, it's highly impossible. I mean, because involving a lot of analytic disk and the computation is not, it's completely weird. So I just reducing the bunch of analytic disk to one analytic disk. And even here, it's very difficult to find a explicit formula for the Kobayashi. Even okay, but you can study more properties very easily here. Okay, so even the one thing is about geometrical properties called geodesics. So the existent geodesic you can get because when you impose the completeness, then there's the theorems called uh, Half-Raynaud theorem in metric geometry. Half-Raynaud theorem says that if you have a complete length space. So here, I mean, there are a lot of notions is that maybe I will discuss some other time what is length space, all those things. Because I'm working in that area. So I will give some other lecture separately for that. Okay, so if you have a complete length space means you have metric space, start with a metric space. You can compute the length of the curve just by the supremum of the uh, all possible partition in the curve. Take the consecutive distance between the points, and you will get then take the supremum over all partitions. You will get a length. Then via length, you know how to define a distance function, right? The infimizing the length of the all possible curves spanning two points, that will become a distance. So if that distance coincides with the original distance, then such a space is called a length space. So ultimately, what you are doing here in the length space, you're just getting the original distance function via computing the length of the curve. Like in Euclidean space, in the Euclidean this metric, you can inherit from the length by computing length of curve with respect to Euclidean norm, right? True now. So the same thing here. So because here we have a norm properties in the Euclidean space, but in general metric spaces it is not there. Okay. So such a space, if the metric space has such properties, such a metric is called length space. Suppose if you have a complete metric space, uh, then any 2 points can be joined by a geodesics. But the uniqueness is not sure there. Okay. So I'm interested to interested to investigate the uniqueness also. So I'm uniqueness, especially for the Kobayashi distance functions. So I'm just reading those kind of stuffs. Yeah, yeah. So
Cool.
I'll be stop here. And any questions or comments?
Thank you very much for the presentation and also the wonderful explanation regarding the big picture of the world of the complex analysis and complex geometry. And yeah, I really love like the way you
Yeah.
summarize this like the very like the big topics, you know. So
Yes.
I just wanna just put some like the comments regarding the just some like the research oriented like the open like the directions. So as you already just explained which direction you are basically interested in. So basically it's just so looking for the kind of alternative to study Kobayashi metric because by the definition, as you said, by its nature, it's very hard to study. So then what's the like the reasonable like the alternative in a way to like the dig some information further? So that's the essential like the question. And the like the lens space and the references, I look at them quite a long time ago. I exactly understand what you're talking like the such as the snow, like the flake, like the domain and that kind of thing related to the boundary geometry. Basically, I also saw
Yeah,
that.
I have a book for the, well, just a minute. I have a book for the metric geometry. It's called Britson book. And is it
Ah,
visible? No, I think.
cool. Yeah,
Britson by, sorry,
yeah,
it's the book. I mean, it's not visible actually.
it's fine.
Maybe,
Uh,
yes, this is called a Britson metric space of non-positive curvature for length space, all those things.
I wanna put just two comments. So it's actually the same, but the about the relation. So one thing is so I'm not sure that you three know like the authors of this like the paper. I don't know. So what I'd like
Britson.
to so I put some like the link on the chat
Um,
screen.
okay, chat.
Mhm. What one like the connection is the Kobayashi metric can be used to study the complex Monge-Ampere equation in the certain like the class. So let me just repeat.
I see.
Yeah, so from the one of the important like, consequence from the Lempert theorem that identify the Cartesian and Kobayashi as you pointed out can be also used to study the like the certain Dirichlet problem of the Monge-Ampere equation. So with the some singularity of the solution whatsoever. So what I wanna point out is that there's a one deep connection between the Kobayashi metric and Monge-Ampere equation. That's one connection I wanna tell. And the another relation from this like the reference this or this also reference that reflect this like the relation. So even your like the recent work I saw it. So is try to study the Kobayashi hyperbolic like the planar domain, and you are looking for the some reasonable like the next like the step of the investigation. And I assume you saw like the green like the function and the green like the metric, that kind of thing are also related in a sense that if you start from the Kobayashi hyperbolic planar domain, then the green function can be used to define certain metric induced from the green like the function. And in fact, those are Lipschitz equivalent in the case of the just a planar domain, as long as it's already Kobayashi hyperbolic. So
Yes.
that your like the result already implies that so if one start from the green function and if the induce like a metric, then it gives a finite like a connected, and you can also play the exact same because the results are topological. So but the green function is the based on the pluripotential like the theory, whereas the place presentation of your side is the related to the complex like the structure. So why I mentioned this? So I'm actually considering to let Jocelyn study in this like the seminar. And what Jocelyn is studying is not directly complex like the planar domain, is kind of the just a boundary. It's a CR boundary, at least for the reason of the class. And in order to, because there's the lack of the complex structure for the CR manifold in general. So one possible alternative is to look at the pluripotential theory in a sense that still this can be also applied for the CR manifold in larger way because the complex structure, there's no complex structure in general on the CR manifold because of the dimension like issue basically. So here's my kind of suggestion. And the reference that you mentioned is directly linked to this like this connection in a way that one should study the boundary data. And in order to study boundary data, one need to choose the sort of the alternative. And you are aiming for that is actually one of the possible like the reason like the trying, in my opinion. So what I will do for in this seminar, in my side to at least introduce the like the link more like the visible way is so I think I need to connect. So what's the like the implication from the Lempert theorem to the complex Monge equation in the case of the domain, convex domain in CN, for example, because we should apply the Lempert theorem first of all, and then what is the consequence in terms of the pluripotential theory, especially when we look at the boundary of the convex domain. And there's a way to just look at the CR like the structure. Then that's the part that Jocelyn also can study. And the question is more actually subtle in a sense that then, so as you look at the like the boundary, like the data with the like the interior of the Kobayashi metric, like the information, then what exactly one should do? So this actual question itself is actually really subtle and difficult. So if one like to establish a correct like the question, then
Correct.
so yeah, we know what to do. But it's in general very like hard to ask the like the reasonable attacking question in a way that how can we really solve? How can we make the progress? That's actually the real like the deeper like part of the
Yeah.
research. So yeah, I really like to so what you actually explain. So yeah, so probably I need time, but I need to like at least like explain the implication from the Lempert theorem to the like the plurality like the potential theoretic like complex Monge
Yes.
point of view. Then Jose can kind of get motivation to look at this kind of
Mm,
things. Yeah, that's what I think I need to do.
mm. Any other comments or questions?
So you can continue to present something next week as well if you are time to prepare, but please do not get overwhelming. So also Ellen can also like present anything as you
Yeah.
might. But I know you two are very busy during the summer, so I don't want to
Yes, yes,
like
yes,
with
yes.
you. So
Actually, I'm writing second paper right now.
yeah. So
Okay,
I
so
will try
it will
to
vary.
prepare the presentation regarding my comment today, but I kind of understand what you're aiming for, so I can kind of try to
Yeah,
provide
yeah.
help.
Thank you.
All right. So I think we can stop the record.